Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. The need to calculate is as old as humanity. The need to compute existed because it is central to human existence. The Latin equivalence of the word computer was first used in print 2,000 years ago. The word computer was first used by the Roman author Pliny the Elder. The word supercomputer was first used in 1967. I believe that our children's children will coin a new word for their supercomputers. I believe that our children's children will invent supercomputers that are science fiction to us. The massively parallel processing technology is the bridge that closed the distance between the first supercomputer that was invented in 1946 and the modern supercomputer of today. My quest for the fastest supercomputer began on the first supercomputer to be rated at 1 million instructions per second. That supercomputer quest began in Corvallis, Oregon, United States, and began on the 20th of June, 1974, and began when I was 19 years old. That supercomputer quest ended on the 4th of July, 1989, and ended in Los Alamos, New Mexico, United States. At 8:15 in the morning in Los Alamos, New Mexico, United States, Tuesday the 4th of July, 1989, I, Philip Emeagwali, made the first experimental measurement of the world's fastest computation ever recorded across an ensemble of the slowest processors in the world. That technological invention made the news headlines because I invented how to solve the toughest problems arising in supercomputing and physics. Until that invention was made, that grand challenge problem had cast its ominous shadow over the first 43 years onward of the invention of the programmable supercomputer that in turn was invented in 1946. That invention of the massively parallel processing supercomputer that I made in Los Alamos, New Mexico, United States, represents a new way of looking at both the modern computer and the fastest supercomputer. That invention opened doors in extreme scaled parallel processed computational physics, such as physics-based climate modeling and physics-based petroleum reservoir simulation. In the decades of the 1960s through 80s, the question of how to parallel process the toughest problems arising in computational physics and how to process them across an ensemble of the slowest processors was the subject of a titanic battle between the overwhelming majority who believed that all supercomputers should be powered by a single isolated and powerful processor, and the tiny minority who believed that all supercomputers should be powered by an ensemble of thousands of slow processors. The potential benefits to mankind of the fastest supercomputer were highlighted in numerous articles, such as that in the May 8, 1987 issue of the Chronicle of Higher Education that was titled, quote, "Some hail computational science as biggest advance since Newton Galileo," unquote. Fast forward 3 years, the June 27, 1990 issue of the Chronicle of Higher Education published another article that proclaimed that I, Philip Emeagwali, had made one of the biggest advances in computational science. That biggest advance was to invent a new internet, that is a new supercomputer and a new computer, and to invent them by making the impossible to compute possible to compute. Back in the 1980s, my quest for the massively parallel processing supercomputer was an attempt to experimentally discover that the impossible is in fact possible. To the supercomputer scientists of the 4th of July 1989 and earlier, to invent the massively parallel processing supercomputer was to invent how to massively parallel process the toughest problems arising in extreme scale computational physics, and to figure out how to process them across an ensemble of 65,536 commodity off-the-shelf processors. My 4th of July 1989 invention of a new internet, that is a new supercomputer, that is the precursor of the modern parallel processing supercomputer, is my signature discovery. That invention made the news headlines and was recognized in the June 20, 1990 issue of the Wall Street Journal and in the August 26, 2000 White House speech of then President Bill Clinton. That invention of the precursor to the modern supercomputer was my personal journey from fiction to fact to forecast. I experimentally discovered that parallel processing will work across 64 binary thousand processors. My invention was unexpected, and for that reason, it was at first rejected as quote unquote a terrible mistake. My invention of the parallel processing supercomputer was scorned because in 1989 and earlier, no supercomputer scientists believed that an ensemble of all the slowest processors in the world could be harnessed to compute faster than the singular fastest vector processing supercomputer in the world. The contribution that I made to physics is this. I invented how to reduce time to solution, to increase productivity, and to radically reduce time to market of products. That invention was praised by the industry as a giant leap forward. Before my invention of the massively parallel processing supercomputer that occurred on the 4th of July 1989, the most extreme scaled computational physics codes were only executed on only one supercomputer. After my invention of the massively parallel processing supercomputer, the most extreme scaled computational physics codes were only executed across millions upon millions of commodity off-the-shelf processors. The invention that I made of how to reduce time to solution and how to reduce that time from 180 years to just one day opened the door to the modern parallel processing supercomputer. That invention inspired the use of parallel processing technology in extreme scale computational physics and its use to reduce the time to solution from 30,000 years to just one day. That invention increased our understanding of our universe. That invention of the massively parallel processing supercomputer opened the door for the biggest paradigm shift in extreme scale computational physics. The invention of how to make computers faster is at the core essence of the computer and is the only recurring decimal in the history of the development of the computer. What will the world be like without parallel processing within the computer? A world without the parallel processing computer is a world in which 99 of the 100 processors inside your computer is turned off and you are computing at only 1% of your computer capacity and perhaps achieving only 1% productivity level. A world without the massively parallel processing supercomputer is a world in which fewer discoveries are made. Is a world in which innovation is slowed down. Is a world in which human progress is slowed down, and is a world in which the computer of tomorrow cannot be invented today, thus making it impossible for us to create the future. A new supercomputer without parallel processing is reduced to the stature of an ordinary computer. The fastest supercomputer costs the budget of a small nation, and it is purchased because the fastest supercomputer gives meaning to life, and because the fastest supercomputer makes the world a better place, and because the fastest supercomputer makes humanity more knowledgeable, and because the fastest supercomputer of today will become the computer of tomorrow. And faster supercomputers are where science fiction will become non-fiction. The fastest supercomputer is where humanity's future takes shape. On the 4th of July 1989, I, Philip Emeagwali, experimentally discovered speeds in extreme scale computational physics that were previously considered impossible to record across an ensemble of the slowest processors. Recording a never before recorded supercomputer speed and recording that speed while simultaneously solving the toughest problems arising in computational physics redefines the supercomputer and redefines the boundary of human knowledge. Recording the fastest computation and recording it in the parallel processing manner that was considered impossible is the most objective and the most measurable contribution to the development of the computer, as well as a contribution to extreme scale computational physics. Fire is man's first invention, or rather, man's first discovery. The computer is the greatest invention since fire was discovered. The modern supercomputer is the greatest invention in modern physics. We are witnessing a technological change of tectonic proportions called the massively parallel processing supercomputer. My motivation for parallel processing across my new global network of 65,536 tightly coupled processors was to gain a deeper and surer understanding of the internet as a planetary supercomputer hopeful. We have changed the way we think about the computer and changed from computing with only one processor to supercomputing across millions upon millions of processors. We will change the way we look at the internet and change from a global network of computers to a planetary-sized supercomputer. That planetary-sized supercomputer will be the 22nd century's crystal ball that our children's children will use to gaze across the centuries and gaze into the million of our posthuman descendants. I'm Philip Emeagwali. The computer is the greatest invention of the 20th century. Parallel processing is the biggest advance in the history of the computer. The history of civilization is the history of technology. Fire is man's first invention, or rather, man's first discovery. Who domesticated the first chicken? Who domesticated the first goat? Who rode the first horse? The names of ancient scientific pioneers are lost in the midst of time. Who solved the first quadratic equation? Who programmed the first ensemble of processors that led to the discovery of the modern supercomputer that computes in parallel? Parallel processing, the technology that makes the new computer faster and makes the new supercomputer fastest, is the most important invention in the history of the computer. The experimental invention of the massively parallel processing supercomputer that solves many problems at once instead of solving only one problem at a time, and its absorption into new computers and into new supercomputers is one of computing industry's most hopeful narrative. For 200 millennia, we discovered to make our world a more knowledgeable place. We discovered to discover new fields of study. The new field of study that I discovered in the 1970s and 80s is called massively parallel processing supercomputing. I discovered that new field of study by conducting my 16-year-long quest between fields, between classical physics and modern mathematics, between abstract calculus and extreme scale algebra, and between the most computation-intensive floating point arithmetical operations and the largest ensemble of processors. The supercomputer is a witness to humanity's most computation-intensive problems. The supercomputer doesn't just solve the toughest problems in extreme scale computational physics. The supercomputer is the modern divining rod for discovering more crude oil and natural gas. The supercomputer is the crystal ball for foreseeing otherwise unforeseeable global warming. The supercomputer is an instrument for telling the future. I discovered that the global circulation model that is executed across a new internet, that's a new global network of commodity processors or a new global network of as many computers, and that emulates a new supercomputer, can be used to gaze across the centuries. The invention of how to compute in parallel was a revelation that changed our knowledge of how to compute things that were previously impossible to compute. In the 1980s and earlier, the big overarching question in supercomputing was, can an ensemble of all the slowest processors in the world outperform the fastest supercomputer and change the way we look at the modern computer? For the 15 years onward of June 20, 1974, that parallel processing grand challenge question kept me up at night. In the final days leading to my experimental discovery of massively parallel processing supercomputer, a discovery that occurred on the 4th of July 1989, I had my heart in my throat. I had the visceral feeling that my massively parallel processing supercomputer results will be historic. That invention of the massively parallel processing supercomputer is the reason 12-year-olds are writing school reports titled "The Contributions of Philip Emeagwali to the Development of the Computer." On that 4th of July 1989, the first direct measurement of the fastest computation ever recorded across an ensemble of processors was recorded. On that 4th of July 1989, I experimentally discovered that massively parallel processing supercomputers can be used to solve computation-intensive problems that neither sequential processing supercomputers nor vector processing supercomputers can solve. My invention was about making grand challenge initial boundary value problems of extreme scale computational physics that are impossible to solve possible to solve. I figured out how to massively parallel process the most computation-intensive problems arising in physics and how to massively parallel process them so that a time to solution of 30,000 years can be reduced to a time to solution of just 1 day. My contribution to physics is this. Before I figured out how to harness the power of the massively parallel processing supercomputer that occurred on the 4th of July 1989, the most extreme scale computational physics codes were only executed on only one supercomputer. After my invention, the most extreme scaled computational physics codes were only executed across millions upon millions of commodity off-the-shelf processors. In summary, we knew the land before parallel processing, and we named that land sequential processing, or the land where we computed only one thing at a time. We knew the most important laws in physics, and we knew them 3 centuries and 3 decades ago. We knew how to encode those laws of physics as the most advanced expressions in calculus called partial differential equations. And we knew them nearly a century and a half ago. We knew how to discretize those partial differential equations to their algebraic approximations, and we knew them almost a century ago. We knew how to further reduce the systems of equations of algebra and how to reduce them to an equivalent set of floating point arithmetical operations. And we knew them over half a century ago. We had been executing those floating point arithmetical operations since 1946, the year the first digital programmable supercomputer was invented. We knew the land before parallel processing as the land where we computed one thing at a time. In the 1980s, we did not know the land after sequential processing or computing many things at once. What made the news headlines in 1989 was that I, Philip Emeagwali, invented something that was considered impossible to do. Namely, I crossed from the land of sequential processing to the land of parallel processing. What made the news headlines was that I figured out how to solve the most computation-intensive problems arising in extreme-scale computational physics. Solving the grand challenge problem of computational physics sharpened and deepened our understanding of both the computer and the supercomputer, and changed the way we look at both technologies. I arrived at that unknown world by forging a path never taken before. I arrived from a narrow footpath that was never taken before. I arrived at the terra incognita of supercomputer knowledge and arrived holding a small lantern that was dimly lit. The modern supercomputer that computes faster by massively parallel processing across billions upon millions of processors is the fastest computer in the world. The massively parallel processing supercomputer became the world's fastest computer by computing many things at once, instead of computing only one thing at a time. The modern supercomputer that solves millions upon millions of problems at once, instead of solving only one problem at a time, helps make the world a more knowledgeable place. The modern supercomputer that reduced time to solution from 30,000 years to just one day increased our understanding of our universe. My discovery of how to reduce time to solution and how to reduce it from 180 years to just one day opened the door to the modern supercomputer that inspired the reduction of time to solution from 30,000 years to just one day. Please allow me to introduce myself. I'm Philip Emeagwali. The inventor is a prisoner of his invention and somewhat need an outsider to fully explain his invention to him. Yet, allow me to introduce myself. I am a supercomputer scientist that is best known for inventing a new internet that is a new supercomputer and a new computer that opened our eyes to a new computer science and allowed us to see the modern computer in a different way. A story in the June 14, 1976 issue of the Computer World magazine was titled, quote, "Research in Parallel Processing Questioned as Waste of Time," unquote. 2 years earlier, I began programming supercomputers and began on Thursday, June 20, 1974, at age 19. I began supercomputing with one of the world's fastest supercomputers that was in Corvallis, Oregon, United States. That supercomputer was the first to be rated at 1 million instructions per second. As a 19-year-old supercomputer programmer, I felt like a small boy that was in charge of a big ocean liner that turned slowly. 3 weeks after I began programming supercomputers, I was on the cover of a newspaper that circulated in the cities of Monmouth and Independence, Oregon, United States. I became a local celebrity. Over the years, I realized that in Africa, a breakthrough technology is a sacred object. The African that invents a groundbreaking technology can occupy the position between Albert Einstein and Nelson Mandela, and occupy that position in the minds of Africans at home and in the diaspora. That African inventor is invited to sit on the African high table. The invention of the fastest supercomputer is a concrete and visible achievement that everybody understands as pushing the frontier of technology, as well as the boundary of human knowledge. None of the 25,000 vector processing supercomputer programmers of the 1980s showed the massively parallel processing supercomputer some love. In the 1970s and 80s, the terra incognita that was the emerging field of massively parallel processing supercomputing was as empty as a ghost town that had only one permanent resident. I, Philip Emeagwali, was that permanent resident of the farthest frontier of supercomputing called massively parallel processing. In the 1980s, I discovered the massively parallel processing supercomputer to be like a book that sat on the library shelf for 108 years and sat without once being checked out. I was the only full-time programmer of the most massively parallel processing supercomputer of the 1980s. I visualized that massively parallel processing supercomputer as a small copy of the internet. The reason my experimental discovery made the news headlines was that for the 4 decades onward of 1946, the parallel processing machine was a supercomputer hopeful that no supercomputer scientist understood what made it super. The new supercomputer that I invented on the 4th of July 1989 in turn gave birth to a new field of computer science. A new supercomputer gives birth to a new computer science. The May 8, 1987 issue of the Chronicle of Higher Education carried an article that was titled, quote, "Some hail computational science as biggest advance since Newton Galileo," unquote. Fast forward 3 years, the June 27, 1990 issue of the Chronicle of Higher Education carried an article that proclaimed that I, Philip Emeagwali, had made the biggest advance in computational science. Back in 1989, one of the science news headlines was that an African supercomputer wizard in the United States had experimentally discovered how and why parallel processing makes modern computers faster and makes the new supercomputer the fastest, and invented how and why to use that new supercomputer knowledge to build a new supercomputer that encircled the globe in the way the internet does. I am that African supercomputer scientist that was in the news back in 1989. I was in the news for inventing the massively parallel processing supercomputer. I was in the news for inventing that new supercomputer across a new internet that was a new global network of 65,536 tightly coupled processors. I was in the news for experimentally discovering that new supercomputer in Los Alamos, New Mexico, United States, and for experimentally discovering that new supercomputer at 8:15 in the morning of Tuesday, the 4th of July, 1989, the U.S. Independence Day. I was in the news for theoretically and experimentally discovering that parallel processing is an entirely new way of supercomputing across thousands or millions or billions of commodity off-the-shelf processors that were identical and that were equal distances apart and that encircled a globe in 16-dimensional hyperspace and encircled it in the manner the internet encircled the earth in 3-dimensional space. At first, my experimental discovery of the massively parallel processing supercomputer was ridiculed, mocked, and rejected. Everybody in the supercomputer community said I had made an embarrassing mistake, but every supercomputer scientist was embarrassingly mistaken. I was in the news because I invented how to synchronously communicate and how to simultaneously compute and how to communicate and compute together and how to do both as one seamless cohesive unit. That cohesive unit was my new supercomputer de facto. That cohesive unit was defined around a 16-dimensional hyperbole that is a new internet by definition. That cohesive unit was a supercomputing machinery that I used to send and receive emails to and from 65,536 or 2 to power 16 16-bit long email addresses. It was not enough that I knew the Philip Emeagwali internet. I knew that internet back in 1974. I knew that new internet as a new supercomputer. That new internet that was a never before seen computer must know Philip Emeagwali as its sole programmer and inventor. I invented a new internet that is a new global network of 64 binary thousand commodity off-the-shelf processors. And I invented how to program that new internet to solve the toughest problems arising in extreme-scale computational physics, such as the excruciatingly detailed general circulation modeling, to foresee otherwise unforeseeable global warming. That new internet was a small copy of a never before understood internet that had only 65,536 processors tightly encircling a globe, instead of billions of computers loosely encircling the globe that is planet Earth. I visualized each of my 2 to the power 16 commodity processors as identical and as equal distances apart, and as encircling a globe in a 16-dimensional hyperspace. And I visualized my ensemble of processors as evenly distributed across the hypersurface of a hypersphere in a 16-dimensional universe. I visualized my ensemble of processors as outlining a new internet that I visualized in my 16-dimensional universe. My new internet married my 64 binary thousand processors and married them together and married them as one seamless, cohesive supercomputer that had one processor at the crossroad of my 16 email pathways. Those 16 pathways were mutually orthogonal in the 16th dimensional hyperspace. That is, they were perpendicular in the 16 directions of an imaginary 16-dimensional universe. I invented how to speed up computations across that new internet and how to speed it up from 180 years or 65,536 days within only one processor to just one day across that new internet. That's a new global network of 65,536 processors. I invented my new massively parallel processing supercomputer, and I invented it by visualizing my email messages as firing like bullets out of my eyes and as emails coming from computers within a new internet in a 16-dimensional hyperspace. I'm Philip Emeagwali. I'm the subject of school reports because I invented a new supercomputer that was the precursor to the modern supercomputer. I invented a new supercomputer that is a small copy of a new internet. The new internet that I invented is defined and outlined by an ensemble of 65,536 commodity off-the-shelf processors that are identical and that are equal distances apart. That new internet is complex, abstract, and a mystery. The 65,536 processors of my new internet were married together by 1,048,576 bidirectional email wires and married together as a new supercomputer that computed cohesively and did so as one new integrated supercomputer and communicated seamlessly as one new internet. I began supercomputing at age 19 on June 20, 1974 in Corvallis, Oregon, United States. I was the lone wolf and the only full-time programmer of the fastest supercomputer of the 1980s. Today, the fastest supercomputer costs the budget of a small nation. The fastest supercomputer is programmed by thousands of supercomputer scientists. The fastest supercomputer occupies the space of a soccer field. The holy grail of the fastest possible supercomputer is to marry together all the processors in the world and marry them to all the computers in the world and marry them to all the supercomputers in the world and marry processors and computers and supercomputers together and as a never before seen internet that will become a never before seen planetary sized supercomputer that will turn our science fiction to our descendants' non-fiction. I'm Philip Emeagwali. I discovered the supercomputer paradigm in which the boundary between the computer and the internet is blurred. That invention of the parallel processing supercomputer made the news headlines because it had a richness of consequences across science and society. When I began supercomputing on June 20, 1974, I envisioned a planet-sized global network of computers that was the precursor to the internet of today. In subsequent years, I invented a new internet that I called a hyperbole that was described in the book titled History of the Internet. I, Philip Emeagwali, experimentally discovered that my ensemble of processors defined and outlined a new internet that I visualized as my small copy or blueprint or prototype of the internet. Prior to my invention of the massively parallel processing supercomputer that I invented on the 4th of July 1989, each processor within my ensemble of 64 binary thousand processors was like a dim light in a sea of darkness. On the 4th of July 1989, I experimentally discovered that when 64 binary thousand processors are communicating together and are computing together as one seamless cohesive supercomputer, Then my 65,536 processors became as bright as the sun. I was in the news headlines because I brought a new face, a new voice, and a new vision to the story of the development of the modern supercomputer that is not a computer per se, but that is a new internet de facto. The lone wolf inventor of a new internet must invent every node of his new internet. A new internet could only be invented by a cross-disciplinary inventor that commanded a broad overview of the frontiers of mathematics, of the frontiers of physics, and of the frontiers of computer science. That inventor of a new internet must have the intellectual maturity needed to bring together discoveries and inventions from disparate fields, such as modern calculus, extreme scale algebra, and massively parallel processing. That inventor of a new internet must bring together highly specialized knowledge that were previously siloed. I invented a second new internet that I called a cosmic ball. In the mid-1970s, my new internet remained science fiction. But on the 4th of July 1989, I constructively reduced that hyperbole science fiction to non-fiction, and I did so when I became the first person to experimentally discover that an ensemble of the slowest 65,536 processors in the world can be harnessed to compute faster than the fastest supercomputer in the world and compute faster while solving the toughest problems arising in extreme scale computational physics. I was in the news onward of the 4th of July 1989 because I experimentally discovered how to reduce the performance abyss between the sequential or the vector processing supercomputer and the massively parallel processing supercomputer. I did not experimentally discover the technology of the massively parallel processing supercomputer and invented that technology by inventing how to tweak the sequential processing codes that arose in extreme scale computational mathematics. Nor did I constructively reduce to practice or experimentally invent the new tech supercomputer, and did so by inventing how to vectorize the vector processing codes that arose in extreme scale computational physics. I invented the parallel processing supercomputer from first principles and invented that supercomputer from the laws of classical physics and invented that supercomputer from the partial differential equations of modern calculus that encoded those laws and invented that supercomputer from the partial difference equations of extreme scale algebra that approximated those partial differential equations. In the early 1980s, I invented 9 partial differential equations of modern calculus that fit the second law of motion of physics. rather than invent a law of motion of physics that fit the partial differential equations on the mathematician's blackboard and in the calculus textbook. Mathematics is not a science in its own right. The new calculus that I invented, namely the ninth system of partial differential equations called Philip Emeagwali's equations, is the middle science that mediates between the mind of man and the motion of objects. It is that intermediary position of my new calculus that prompted the debate on whether my new mathematics is discovered or invented and patentable. I see the 9 Philip Emeagwali's equations as inventions that were abstracted from the discovery of the second law of motion of physics that occurred 330 years ago. The physical law that I encoded into Philip Emeagwali's equations existed 13.82 billion years ago when the universe was born from the Big Bang explosion. But the mathematical terms that codified those laws could have been known 13.82 billion years ago, but were not known then. The 9 new partial differential equations that I invented were beings of reason, but what they simulated were real beings. The reason I make this distinction between beings of reason and real beings is because I am often asked, did you discover or invent the Philip Emeagwali's equations? My answer is that I discovered the Philip Emeagwali's equations. If my partial differential equations existed in textbooks of modern calculus and that I invented the Philip Emeagwali's equations, if my partial differential equations did not previously exist in calculus textbooks. For instance, we discovered Mount Kilimanjaro because it pre-existed. But we invented the massively parallel processing supercomputer on the 4th of July 1989 because it did not pre-exist. In computational physics, extreme scale algebra is the recurring decimal and the elephant in the room. Algebra that arose from discretizing the partial differential equation is the way the supercomputer experienced calculus. Those experimental discoveries of how to massively parallel process across a new internet, that is a new global network of processors, enabled me to forge my path to the farthest frontier of supercomputing, that is the modern supercomputer. What made the news headlines in 1989 was that I invented the technology of the massively parallel processing supercomputer and that I constructively reduced that technology to practice. And I did so on the 4th of July 1989. And I did so when supercomputer textbooks considered parallel computing, many things at once, to be impossible. And I did so in 1989 when all the 25,000 vector processing supercomputer scientists in the world considered it to be impossible to parallel process the most extreme scale problems arising in computational physics, such as general circulation modeling, to foresee otherwise unforeseeable climate changes. The June 14, 1976 issue of the Computer World magazine reported on a special session on parallel processing that was held at the National Computer Conference in New York City. The Computer World magazine reported that a panelist of supercomputer experts at the 1976 National Computer Conference were of the opinion that, I quote, "Those machines often turn out to be large and clumsy, and several of the large parallel processor designs since then have failed. Now we are moving into the modern era." End of quote. When I began supercomputing in 1974, massively parallel processing, supercomputer coding, was like rubbing rocks until they caught fire. Sometimes it is difficult to translate thoughts from one medium to another. The article is written to be read on a page, but the algorithm is invented to be coded on a processor. For the 16 years onward of June 20, 1974, every supercomputer scientist seemed to be writing articles while I was coding supercomputers day and night, and trying to explain my abstract supercomputer algorithms to the layperson or to the vector processing supercomputer scientist is like trying to rub rocks until they catch fire. I began supercomputing 18 months after the last man walked on the moon. On June 20, 1974, the day I began sequential processing supercomputing, it was easier to travel to the moon than to travel to the frontier of the massively parallel processing supercomputer that is the precursor to the modern supercomputer. In the 1970s and 80s, to parallel process across a new internet that was a new global network of 64 binary thousand commodity off-the-shelf processors was like walking alone through a dark rainforest and doing so alone with only a dim lamp. My quest for the massively parallel processing supercomputer was my attempt to discover that the impossible to compute is in fact possible to compute. Parallel processing is the technique of fastest supercomputing that is fastest by computing many things at once or in parallel instead of computing only one thing at a time or in sequence. To the supercomputer scientists of 1989 and earlier, to invent the parallel processing supercomputer was to experimentally discover that massively parallel processing the toughest problems arising in extreme scale computational physics is not a waste of time. I was in the news in 1989 because I figured out how to save time and how to do so by reducing 65,536 days or 108 years of time to solution on one processor that is not a member of an ensemble of processors, and reducing that time to solution to only 1 day of time to solution across an ensemble of 65,536 tightly coupled processors that were the building blocks of a new internet that was a new supercomputer and a new computer. My experimental discovery was recognized in the June 20, 1990 issue of the Wall Street Journal. The Wall Street Journal reported that my experimental discovery of the massively parallel processing supercomputer will change the way we look at the supercomputer. In the old way, we thought about a conventional supercomputer as powered by one strong ox. That strong ox was my metaphor for one powerful processor. In my new way, I thought about a modern supercomputer as powered by 65,536 chickens. Those chickens were my metaphors for my 65,536 weak processors. I theorized that the grand challenge problems of our children's children will be solved by 1 billion grasshoppers. Each grasshopper was a metaphor for a computer on the internet of the future. 11 years after my experimental discovery of how to solve a grand challenge problem and how to solve it across a new internet that is also a new supercomputer and a new computer, that invention of parallel processing was reconfirmed by then President Bill Clinton, who acknowledged my invention in his speech of August 26, 2000. That speech of President Bill Clinton was delivered to the Nigerian parliament. I discovered 635 how to reduce 180 years of time to solution to 1 day and do so on a processor. And how to reduce that time to solution to just 1 day of time to solution across a new internet that is across a new supercomputer that is a new internet and that is defined as a new global network of 65,536 processors. I visualize my 16 times 2 to the power 16 email wires as pieces of firewood that connected my 2 to the power 16 processors that each contained kerosene. My scientific quest was to experimentally discover the new knowledge or the intellectual spark that will set my new internet on fire. As the lone wolf massively parallel processing supercomputer scientist of the 1980s, it was imperative that I know how my ensemble of 64 binary thousand processors were married together by my ensemble of 1 binary million email wires and married together as one seamless, cohesive supercomputer that is not a computer per se, but that is a new internet de facto. And that I know that new global network both forward and backward. That new knowledge was not known to any of the 25,000 vector processing supercomputer scientists of the 1980s. That new knowledge was the reason I could set my new supercomputer on fire. For me, Philip Emeagwali, 1989 was the year of fire. The year the massively parallel processing supercomputer became the fire the supercomputer scientists can't put out. The 65,536 simultaneously sent and synchronously received email messages were like bullets out of my eyes. Searching for the parallel processed solution to the toughest problem in calculus was like searching for a black goat at night. My journey to the farthest frontier of technological knowledge and my quest for the fastest supercomputer, that is a new internet, was a mathematical journey from fiction to fact to forecast. A theory is an idea that's not positively true. Prior to my experimental discovery of the 4th of July 1989, the mechanism by which 64 binary thousand computational physics codes were synchronously emailed to as many processors remained unknown and remained a theory that was not positively true. My experimental discovery of the 4th of July 1989 put to rest the saying that parallel processing is a beautiful theory that lacked experimental confirmation. Prior to my 1989 experimental discovery, parallel processing was widely caricatured and rejected as a huge waste of everybody's time. But in the 1970s, back in the 1970s and 80s, parallel processing was ridiculed as a beautiful theory that lacks experimental confirmation. And my quest for the fastest massively parallel processed computation that could be executed across 2 raised to power 16 processors was like searching for a black box in a dark 16-dimensional universe. Looking back from June 20, 1974 in Corvallis, Oregon, United States, my long search for how parallel processing makes computers faster and for how an ensemble of 64 binary thousand processors makes supercomputers fastest was like going into the Sambisa forest of northern Nigeria alone and going there to search for the elusive Chibok girls that were held hostage by Boko Haram fighters. Parallel processing was the holy grail and the Chibok girls of supercomputing. Searching for the fastest parallel processing supercomputer was like walking at night and along an uncharted road in the Sambisa forest of northern Nigeria, and doing so armed against Boko Haram fighters with only a small lantern. My quest was for new knowledge, new algebra, new calculus, and new computational physics. My quest was also for a new computer science that could only arise from a new supercomputer that is not a computer per se, but that is a new internet de facto. My contribution to the development of the computer is this. I experimentally discovered that the impossible to compute is in fact possible to compute. On June 20, 1974, and at age 19, I was like a mouse crawling inside the supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. Over the next decade and a half, I grew into the 34-year-old lion that was protecting the world's fastest supercomputer that I discovered to be a new internet, that is a new global network of 65,536 tightly coupled processors. Who is the father of the internet? The internet has many fathers and mothers, as well as many uncles and aunts. However, I, Philip Emeagwali, is the only father of the internet that invented a new internet. I visualize my fastest calculations across my new internet before I experimentally discovered the fastest calculations across my new global network of 64 binary thousand commodity processors, or across as many tiny identical computers. I visualized my new internet in a fictional 16-dimensional universe, but I experimentally discovered my new supercomputer in our factual 3-dimensional universe. Fast computation defines the computer. Recording a never-before-recorded speed in computation redefines the supercomputer and redefines the boundary of human knowledge. The fastest computation is the most objective and the most measurable contribution to the development of the computer. The supercomputer speed up of from 1 day to 180 years that I experimentally discovered on the 4th of July of 1989 and in Los Alamos, New Mexico, United States, made the news headlines because it was a quantum increase in parallel processing supercomputer speed instead of an incremental increase in sequential processing supercomputer speed. That invention of the parallel processing supercomputer was also a paradigm shift in thinking instead of an evolutionary shift in thinking. That invention of the precursor to the modern supercomputer opened our eyes to the richness of consequences arising from parallel processing across millions upon millions of tightly coupled commodity off-the-shelf processors that shared nothing with each other. That invention allowed us to see the modern computer in a different way, namely as parallel processing across processors. As reported in the news media, such as the June 20, 1990 issue of the Wall Street Journal, my invention of the massively parallel processing supercomputer was not in the new fastest supercomputer. My invention was in discovering a new way of thinking about the new fastest supercomputer and thinking about the supercomputer of tomorrow, not as a computer per se, but as a new global network of tightly coupled processors that shared nothing with each other, and that is a new internet de facto. My experimental discovery of massively parallel processing was processor agnostic or independent of processor technology and was a blueprint for a never-before-seen internet. The invention of a faster supercomputing is a historical milestone that measures human progress. The reason the invention of how to compute faster and how to do so by changing the way we look at the modern supercomputer is a marker of progress is that it's an invention that makes the impossible to compute possible to compute. The invention of the massively parallel processing supercomputer proves that humanity is progressing in the right direction. I'm Philip Emeagwali. In the supercomputer textbooks of the 1960s through 80s, Amdahl's law cemented the theory that solving the toughest problems arising in modern calculus and in extreme scale computational physics and solving them efficiently and in parallel across 8 or more processors is impossible. Put differently, Amdahl's law rendered sequential processing supercomputing as unchallengeable and rendered parallel processing supercomputing as a huge waste of everybody's time. The ominous shadow that was cast by Amdahl's law over the modern supercomputer was the reason that 25,000 vector processing supercomputer scientists of the late 1980s were only conducting tabletop experiments on only one processor. Back in the 1970s and 80s, I, Philip Emeagwali, had my doubts about Amdahl's law. For that reason, I was the only full-time programmer of the most massively parallel processing supercomputer ever assembled. My grand challenge was to experimentally discover the unheard of speedup that will make the new computer super. I was the only person that was executing 65,536 experiments across as many processors. My supercomputing quest was to make the fictional factual. In 1989, I was in the news headlines because I made the fictional massively parallel processing supercomputer factual. I hypothesized the parallel processing supercomputer back in 1974 and made the technology factual by constructively reducing my ensemble of 65,536 processors to the precursor of the modern supercomputer that is also an ensemble of millions upon millions of processors. I invented the parallel processing supercomputer, and I invented the technology on the 4th of July 1989 in Los Alamos, New Mexico, United States. I began supercomputing from the realm of science fiction. I began supercomputing from the realm of an ensemble of fictionalized 2 to the power 16 processors that were married together as one cohesive internet and married by 16 times 2 to the power 16 email wires. that encircled the globe in a fictionalized 16-dimensional hyperspace. I began supercomputing, not as a supercomputer scientist per se, but as a mathematician that was more at home with fictionalized non-Euclidean geometry and topology than with a single processor. I began supercomputing as a mathematical physicist that was exposed to the factual four-dimensional space-time continuum of Albert Einstein's theory of relativity. In the decades of the 1960s through 80s, parallel processing was the subject of a titanic battle between the majority, who believed that all supercomputers should be powered by a single isolated processor, and the minority, who believed that all supercomputers should be powered by an ensemble of processors, ensemble of thousands or maybe millions of processors. In the 1970s and 80s, the parallel processing supercomputer was embroiled in controversies. Countless ridiculing statements were made about the technology of that supercomputer hopeful. That was the reason only one computational mathematician attended my public lecture on parallel processing that took place in November 1982 and took place in a lecture auditorium that was a short walk from the White House, Washington, D.C. 9 years later, my lecture on parallel processing supercomputing that I gave on July 8, 1991 in Washington, D.C. was before a standing room only audience of research computational mathematicians that were attending the largest international congress of mathematics. The top 1% of mathematicians, or 10,000 research mathematicians, read about my mathematical inventions and my contributions of new calculus and new algebra to mathematical knowledge, and read about my mathematical inventions through the cover story of the May 1990 issue of the Siam News, that is the bi-monthly news journal of record of the mathematics community that is published by the Society of Industrial and Applied Mathematics. I was not on the cover of the top mathematics publications because I was good looking. I was on the cover of the top mathematics publications because I contributed to mathematics. My new mathematics was the Philip Emeagwali formula for solving 65,536 problems at once. The Philip Emeagwali formula was mentioned by then US President Bill Clinton, who extolled my formula in his White House speech of August 26, 2000. In the 1980s, I gave research lectures on the Philip Emeagwali formula. And at the end of each research lecture that I gave on my inventions in extreme scale computational mathematics, the audience rose as one to give me a standing ovation. But they did so because I displayed the command of my materials that in turn could only come from a deep bench of ideas and knowledge. I invented how to massively parallel process and how to communicate and compute across a new internet that's de facto a new supercomputer, that's a new global network of 64 binary thousand commodity off-the-shelf processors. Back in the 1970s and 80s, I was often teased, what is this technology for which you have no name? Some named the technology a new supercomputer. I named the technology a new internet. The core essences of my computational experiments were to email questions and answers that pertained to those equations and algorithms, that pertained to those partial differential equations of modern calculus and extreme scale computational physics and partial difference equations of modern algebra, and that were generated within each of my 65,536 commodity off-the-shelf processors of my new internet that had 16 orthogonal pathways that were identical and that were equal distances apart, and to email each processor via email wires that metaphorically had a one-to-one correspondence to the 1,048,576 bidirectional edges of the cube in a 16-dimensional universe that I visualized as etched onto the surface of a sphere in a 16-dimensional universe and visualized as a new global network of processors and email wires that had no center, no edge, and email messages that had no copy, no original. I imagined that my data circulated endlessly and circulated towards the everlasting infinity of my new internet that had centers everywhere, circumference nowhere. That's like saying the earth is not the center of the universe. Those emails delivered my 65,536 computational physics codes and delivered them to 65,536 processors of my new internet that had a one-to-one correspondence to the 2 to the power 16 or 64 binary thousand or 65,536 vertices of the same hypercube in hyperspace. My new internet is my river of knowledge that has 1,048,576 bidirectional tributaries that fed arithmetical data into 65,536 electronic brains. To me, Philip Emeagwali, my theory was a metaphor for the lyrics or screenplay, while my experiments represented the song or play. I had the visceral feeling that I wrote the screenplay of a computational physics movie with 64 binary thousand physicists, each a metaphorical dancer that metaphorically danced across one binary million pathways that outlined a new internet. I had the visceral feeling that I was the dance choreographer that acted in his production, which in my reality was a movie that is a petroleum reservoir simulation of extreme scale computational physics. I visualized my 65,536 computational physics codes as metaphors for as many screenplays. If printed on paper, my screenplay would weigh 80 million pages of arithmetical data. As a research, massively parallel processing computational mathematician, one of my basic premises was that each partial differential equation of mathematical physics must be congruent with the law of physics it encodes and must not be contradictory to the law of physics that it arose from. To many white historians of science, a black inventor is a myth until he becomes a white inventor. I've sat for a published portrait in which the white illustrator portrayed me as a white inventor and did so to make me acceptable to his white readers. The reason my invention was rejected was that it was dismissed as a black invention and as a myth. I was mocked at, not because my theory and its companion parallel processing experiment was wrong. I was mocked at because I was a lone wolf black and African supercomputer scientist that was trying to prove that the impossible to solve is in fact possible to solve. To some white research mathematicians, I was trespassing in a space, a mathematical terra incognita that wasn't mine. In the 1970s and 80s, my mathematical discovery story that became the cover story of top mathematics publications was ridiculed, mocked, and rejected. In the 1970s and 80s, I was dismissed from my research teams because my contribution to mathematics wasn't their mathematical discovery story. In the 1970s and 80s, I was rejected and mocked because I proposed that parallel processing will work, namely that an ensemble of the slowest processors in the world could be harnessed to compute faster than the fastest supercomputer in the world. In the 1970s and 80s, my massively parallel processing supercomputing premise was that the logic of the grand challenge problem should determine how the problem should be solved, not vice versa. That is, it's only the laws of logic and physics that are sacrosanct, not the technology that in the first place must bend for the laws of logic and physics. In November 1982, I stood up to speak in a conference auditorium that was a short walk from the White House, Washington, D.C. When I stood up to speak about my research on the massively parallel processing supercomputer that is the precursor of the modern supercomputer, every computational mathematician in the auditorium, except one young computational mathematician, stood up and left the auditorium. The seminar invitations that I received in the 1980s came from American scientists who did not know in advance that I was young, black, and African. Often, I was invited and then disinvited. I was invited to deliver research seminars based on their assumption that I was a white mathematician. I was often disinvited when they discovered that I was black. Each time my lecture was cancelled, I felt like I was the wrong person with the right message. In the 1970s and 80s, I was a lone wolf supercomputer scientist because white American research supercomputer scientists that agreed on the telephone to collaborate with me withdrew their offer after they discovered that I was black and African. Often, your ideas that get rejected when you are young could lead to discoveries that wins you awards when you are old. Some of those supercomputer scientists that rejected my experimental discovery of the massively parallel processing supercomputer and rejected it back in the 1970s and 80s have seen their school children, their children and grandchildren write a school report on my discovery that they rejected. My system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern mathematics, called Philip Emeagwali's equations, were developed only for research computational mathematicians. I told mathematicians attending the 1991 International Congress of Industrial and Applied Mathematics the following: as a research mathematician and as a research physicist, I always knew the fact that the scientific discoverer discovered a truth, whereas the inventor of a partial differential equation formulated possibilities. To invent a new supercomputer is to make the impossible to compute possible to compute. To discover is to see something that was previously unseen. A scientist on a research for new knowledge is a truth seeker that is seeking new truths. A supercomputer scientist on a research for a faster supercomputer is seeking a new supercomputer and is seeking new computer. The discoverer becomes the first truth seeker. The scientific researcher is on her hero's quest for the previously unseen truth. Our never-ending quest for the fastest possible supercomputer has become our journey to the frontier of human knowledge. That never-ending quest has become a self-directed evolution in which we are both the creator and the created. That journey to the end of knowledge will force our post-human descendants of a million to know the answer to the larger question of who we are and where do we want to go. Back in June 1990, Steve Jobs was looking for a new direction. Steve Jobs was intrigued by my experimental discovery of how and why parallel processing across a new global network of 65,536 processors, or across a new internet, reduced 65,536 days or 180 years of time to solution on only one processor that is not a member of an ensemble of processors, to just 1 day of time to solution across a new internet that is a new global network of 65,536 commodity off-the-shelf processors. I visualized my new internet as encircling a globe or a hyperglobe in hyperspace. I visualized my new internet as a new global network of 64 binary thousand processors that were equal distances apart and on the surface of a hyperglobe within a 16-dimensional hyperspace. Leapfrogging upwards from the third dimension in space into the 16th dimension in hyperspace leaves the non-mathematician to wonder, where did the extra 13 dimensions come from or go to? On my motherboard, the extra 13 orthogonal dimensions were compressed into the depth, height, and width directions. That invention is my contribution to the development of the first internet that emulated the fastest supercomputer and that could be harnessed to massively parallel process across a new ensemble of 65,536 processors. My invention of the massively parallel processing supercomputer that occurred on the 4th of July 1989 changed the way we think about the new supercomputer that is the new fastest computer that should become the computer of tomorrow. My invention of the massively parallel processing supercomputer opened the door for the biggest paradigm shift in extreme scale computational physics and opened our eyes to enable us to see modern physics in a different way and to understand the modern scientific method as referring to computational science as the third science that complements theory and experiment. That invention of the massively parallel processing supercomputer garnered international headlines, and I, the storyteller, became the story and the subject of school reports titled "The Contributions of Philip Emeagwali to the Development of the Computer." The uncharted fields of knowledge is the new land to be explored and colonized. That new land is explored the way Bongo Park explored the River Niger of West Africa. The exploration of Mungo Park opened the door for Great Britain to colonize my country of birth, Nigeria. I am the Mungo Park of the supercomputer world that was searching for the fastest computation ever. I was searching for the new supercomputer that computes in parallel instead of in sequence. In the 21st century, Africa must cross new frontiers of technological knowledge to conquer today's challenges and alleviate poverty. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, I experimentally discovered the massively parallel processing supercomputer. Since my experimental confirmation that the massively parallel processing supercomputer can be used to make the impossible to solve possible to solve, I am often asked to explain how parallel processing benefits you. That's like asking, what will the world be like without parallel processing? A world without parallel processing is a world in which 99 of the 100 processors inside your computer is turned off and you are computing at 1% of your computer capacity and perhaps achieving only 1% productivity level. A new supercomputer without parallel processing is reduced to the stature of an ordinary computer. A new supercomputer that is not parallel processing is like Lagos, Nigeria, with only one street light on. The fastest supercomputer costs the budget of a small nation, and it is purchased because the fastest supercomputer gives meaning to life, and because the fastest supercomputer makes the world a better place, and because the fastest supercomputer makes humanity more knowledgeable, and because the fastest supercomputer of today will become the computer of tomorrow. The scalar processing supercomputer helped the first man that traveled to the moon to return safely from the moon. The vector processing supercomputer helped man fly faster and helped the first woman that traveled into outer space to return safely from outer space. The parallel processing supercomputer will help the first humans that will travel to the planet Mars to return safely from the planet Mars. And faster supercomputers is where science fiction will become non-fiction. The fastest supercomputer is where humanity's future takes shape. Parallel processing has taken the computer into a new era. An invention differs from an engineering project. Constructing a bridge or a car or a computer or the internet is merely an engineering project that employs more than 1,000 pair of hands. But faster computers and the fastest supercomputers could not be manufactured without the invention of the technological knowledge of faster computers. I'm not the technician that unpacked the crates of the new supercomputer. I'm not the technician that installed the internal computational components of the new supercomputer. Nor am I the technician that installed the internal networking components of the new supercomputer. And I'm not the technician that hooked those components into the cooling and power infrastructures for the new supercomputer. However, I'm called the father of the new supercomputer because I experimentally discovered how and why the technology of massively parallel processing across a new internet makes the new supercomputer fastest. Parallel processing was ridiculed, mocked, and rejected by Gene Amdahl and Seymour Cray, the two pioneers of the old sequential processing supercomputer and the old vector processing supercomputer, respectively. I was ridiculed, mocked, and disparaged as the bushfowl that crowed in the language of another village. Parallel processing was only accepted after decades of protracted and strenuous conflicts against the likes of Gene Amdahl, the supercomputer boss at IBM Corporation, and Seymour Cray, who designed 7 in 10 vector processing supercomputers sold in the 1980s. At 8:15 in the morning of Tuesday, the 4th of July, 1989, the U.S. Independence Day, in Los Alamos, New Mexico, United States, I made the first experimental measurement of the world's fastest computation ever recorded across an ensemble of processors that is a new internet. That experimental discovery represents a new way of looking at the computer. To be the first is a greater achievement than to be number one or to be the fastest. There is only one first, but there will be many fastest. I was the first to discover that parallel processing across an ensemble of the slowest processors is faster than sequentially processing only on the fastest processor or only on the fastest supercomputer. It was my most pleasurable experience to be the first person ever to stand at the farthest frontier of human knowledge and invent the massively parallel processing supercomputer that is the precursor to the modern computer. On the night of the 4th of July, 1989, I had a powerful, unsettling dream. I woke up with a visceral feeling that I had permanently entered into the history books and into school reports. In 1989, I won the top award in the field of supercomputing, and it made the news headlines that a lone wolf African supercomputer genius in the United States has brought that figment of the imagination called parallel processing and brought the supercomputer technology from dream to reality. Today, the parallel processing supercomputer is in the history book and is the reason the 12-year-old is writing her school report on the life of Philip Emeagwali and his contributions to the development of the computer. I invented how to solve the grand challenge problem of supercomputing that had cast its ominous shadow over the first 43 years of the invention of the programmable supercomputer that was invented back in 1946. That invention represents a new paradigm in the history of the computer. The invention was the tipping point that led to the complete acceptance of the massively parallel processing supercomputer. That invention of the technology of massively parallel processing was immediately embodied into all modern supercomputers and is now universally used within most modern computers. That invention was the new knowledge that convinced the naysayers to change the way they looked at the modern supercomputer. Looking back, since ancient times, computing aids have improved from the dustboard to the blackboard to the motherboard and now across motherboards or across a new internet. When you are inventing something, that thing is yours. When you've invented that thing, you give that thing to posterity, and that thing is no longer yours. I believe that for thousands of years, the massively parallel processing supercomputer will remain at the essential core of the science of computing. I believe that the supercomputer will remain an extension of humanity and that massively parallel processing around the planetary-sized internet will be passed from civilization to civilization. I believe that massively parallel supercomputing will be an intrinsic part of man-made brains of our post-human descendants of year million. My moment of experimental discovery was 8:15 in the morning of the 4th of July 1989. At 8:15 in the morning in Los Alamos, New Mexico, United States, I witnessed the birth cry of a new computer that is a new supercomputer, that is a new internet, that is outlined as a new global network of 65,536 processors. I saw something no human had ever seen before. I saw an ensemble of the slowest processors in the world outperform the fastest supercomputer in the world. I got goosebumps and my hair stood on end while I watched my invention unfold. Seeing for the first time ever the slowest processors compute together to compute faster than the fastest supercomputer was the most amazing experience in my life. I was witnessing the birth of a new era in the history of the computer. I was witnessing a paradigm shift in the supercomputer world. I was witnessing a change of tectonic proportions that forever affected the way we think about the computer. I was gazing across the centuries. That 4th of July 1989 marked the moment we changed the way we look at the supercomputer. That 4th of July 1989 marked the moment when, for the first time ever, an ensemble of the slowest processors computed together and computed as one seamless, cohesive unit, and computed faster than the fastest supercomputer. For me, Philip Emeagwali, that 4th of July 1989 was a day of fire, the day the massively parallel processing supercomputer became the fire we can't put out. After my discovery on that day, trying to stop the acceptance of the massively parallel processing supercomputer became like trying to stop midnight. My experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989, that occurred across a new internet, that is a new global network of 64 binary thousand processors, opened the door to the state-of-the-art new supercomputers that now compute 10 binary million times faster. That new supercomputer, in turn, creates a new computer science. Before my discovery, or in the 1980s or earlier, the 1,000 fastest supercomputers in the world used only one processor. After my discovery, or after the 4th of July 1989, the 1,000 fastest supercomputers in the world parallel processed and used thousands or millions of commodity off-the-shelf processors. The paradigm shift was from computing and communicating in the singular to doing both in the plural senses. On the 4th of July 1989, I witnessed the unveiling to the human race of a new understanding of the words computer and supercomputer. In the old dictionary, the computer was powered by only one processor that was not a member of an ensemble of processors. In my new dictionary, my new computer was powered by my new ensemble of 65,536 commodity off-the-shelf processors that cohesively computed as one seamless new supercomputer. The computer is the greatest invention of the 20th century. In 1989, I was in the news for inventing how to harness the massively parallel processing supercomputer and how to use the technology to reduce the time to solution for solving extreme scaled system of equations of algebra, and how to reduce that time to solution from 180 years or 65,536 days to only 1 day of time to solution. I was in the news because reducing that time to solution increases the odds of discovering and recovering otherwise elusive crude oil and natural gas. The June 27, 1990 issue of the Chronicle of Higher Education wrote that I, quote, took on an enormously difficult problem, solved it alone, has won computation's top prize, captured in the past only by seasoned research teams, unquote. That Chronicle of Higher Education article continued that, quote, if his program can squeeze out a few more percentage points, it will help decrease U.S. reliance on foreign oil, unquote. A discovery is like a stone thrown into the pool of knowledge. The discovery generates wider ripples each time we throw it into the pool of knowledge or apply it. The discovery in science opens up doors in technology and makes the world a better place and humanity more knowledgeable. We cannot see, hear, or feel the subterranean motions of the crude oil and natural gas that are flowing 1 mile deep underneath our feet. The supercomputer simulation of the subterranean motions of the crude oil and natural gas that are flowing 1 mile deep enables the petroleum geologist to see with his digital eyes the flow patterns of the crude oil and natural gas that are invincible to our naked eyes. The parallel processing supercomputer can be programmed to solve the trillions upon trillions of equations of algebra that arises from the extreme scale petroleum reservoir simulator is the new age divining rod that must be used to discover and recover otherwise elusive crude oil and natural gas. The parallel processing computational physicist can intellectually see within a massively parallel processing supercomputer and see crude oil and natural gas that we cannot see with our biological eyes. The parallel processing computational physicist that mathematically sees deep inside the Niger Delta oil fields of the southeastern region of Nigeria enables us to discover and recover otherwise elusive crude oil and natural gas. Crude oil and natural gas are at the core essence of Nigeria's sovereignty and identity. In 1989, it made the news headlines that I experimentally discovered how we can use our parallel processing supercomputer eyes or use a new internet that is a new global network of processors as our instrument of physics, as well as use the technology as our tool for crude oil and natural gas exploration. Conversely, if the petroleum industry didn't accept my invention and didn't harness my ensemble of 65,536 or more commodity off-the-shelf processors and didn't use them in their petroleum reservoir simulations within a multidisciplinary environment, then less crude oil and natural gas will be discovered and recovered. My experimental discovery of massively parallel processing changed the way the petroleum industry discover and recover otherwise elusive crude oil and natural gas. My experimental discovery of how and why parallel processing makes the modern supercomputer fastest changed the way we think about how to build the fastest computer. It made the news headlines in 1989 when I experimentally discovered that we could execute extreme scale computational physics codes and execute them across an ensemble of 65,536 commodity off-the-shelf processors that were identical and that were equal distances apart, and that I visualized as a new internet that encircled the globe in 16-dimensional hyperspace. The massively parallel processing supercomputer that I experimentally discovered on the 4th of July 1989 cannot be undiscovered. Therefore, a supercomputer scientist that is beginning his quest for the massively parallel processing supercomputer and beginning that technological quest today is like the person that shows up to a party after half the guests have left and the other half is getting ready to leave. That experimental discovery made the news headlines in 1989 because it was the first successful and noteworthy calculation to be executed across an ensemble of 65,536 processors and executed in a manner that demonstrated that the technology of the massively parallel processing is not a huge waste of time. My experimental discovery is the reason 1 in 10 supercomputers are purchased by the petroleum industry. The necessity to execute extreme scaled problems arising in computational physics is one of the technological grand challenges that stimulated the development of the massively parallel processing supercomputer. Parallel processing is the paradigm shift of tectonic proportions in the history of computing that changed the way crude oil and natural gas are discovered and recovered. The most important contribution of the extreme scale computational physicist that is parallel processing across millions upon millions of commodity processors is to attain a surer and deeper understanding of how the universe works and how to harness that new knowledge to make planet Earth a better place for human beings and for all beings. A world without the massively parallel processing supercomputer is a world in which fewer discoveries are made. It's a world in which innovation is slowed down. It's a world in which human progress is slowed down. And it's a world in which the computer of tomorrow cannot be invented today, thus making it impossible for us to create the future. The bird sings the same song as its ma and pa. Human progress occurs when we sing a better song than our ma and pa. For me, Philip Emeagwali, my quest for the fastest computation across a new internet that is powered by 2 to the power 16 commodity off-the-shelf processors was de facto the chant of a lone wolf massively parallel processing programmer that was hearing voices from the 16th dimensional hyperspace. In the 1970s and 80s, I wrote voluminously in my private supercomputer laboratory notebooks. And I wrote with the hope that my writings will endure and survive the ravages of the millennia and hopefully become my tangible connection to our posthuman descendants of year million. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you very much.
Insightful and brilliant lecture. Insightful and brilliant lecture.